So I'd like to briefly go over the numerical results that we generated for this paper so that we're able to appreciate the capabilities of toPSAil, and potentially this would be useful for your future usage using toPSAil to explore your own different projects. So we actually set the relative and absolute tolerance for the ODE solver as the 10 to the minus 3 and 10 to the minus 6. And we define cyclic steady state at which the squared L2 norm of the difference between the initial and final condition vectors are 10 to the minus 8. And we normalize that by the total number of states in the vector as well. So I didn't really talk about cyclic steady state, but basically what it is that cyclic steady state means, since this is a dynamic and cyclic process, there's no no steady state, right? Because things constantly change in time, but it's cyclic. So when we actually compare the beginning of the cycle with the end of the cycle, and if that difference is approaching like small, tiny, like residual, right? If the difference is increasingly getting smaller, then we can think of it as, reaching some sort of steady state and the cyclic steady state. So cyclic steady state as in being able to return to the original state at which you begin your cycle. So enough with cyclic steady state. Let's first delve into the numerical results. The first one, we looked into the paper from Kager and Neighbor. Kager and Neighbor, Dr. Neighbor from Ohio State University, and they studied the equilibrium theory for PSA. So assuming there's no mass transfer resistance, how can PSA process perform? That was the main question that they were trying to answer, right? So in this case, basically in our simulator, we chose mass transfer coefficients in our model to be pretty big so that there's little to no mass transfer resistance, so that we're able to understand the behavior and mimic the equilibrium theory. So when we simulate ideal PSA process, meaning near equilibrium, we see that this is two column simulations. So column 1 is in dark line and then gray line column 2. So repressurize, and the other column depressurize, and then undergo high pressure feed in the first solver, but then you do the depressurization and purge, then you repressurize and depressurize, and then the second column goes to the high pressure feed. You can kind of see that even though the two columns are operating in a discrete and cyclic way, the production phase or the high pressure feed is continuous, right? Because you have two columns making up for the downtime of each other. This is the gas phase SR phase concentration profile at the end of the high pressure feed for the first SR. You can kind of see all these flat line means they're in equilibrium with the feed. So with the feed being the air, 21% oxygen and assuming 79% nitrogen, although that's not quite precise. When we saturate our adsorbent, geolite 5A, with air, we have this following SR phase concentration. But then you see that there's tiny bit of mass transfer zone right here. And then that's where actually the gas exchange is happening, right? And then you see that this mass transfer zone is almost at the tip of the product end of the column. So its breakthrough is happening. So this is kind of the picture towards the end of the high pressure feed where you need to stop and then depressurize. Because all these adsorption capacities are depleted, right? They're saturated with the feed, which was air. And you can kind of see the difference in the gas phase concentration and then the influence of the number of CSTRs. 10 CSTRs, 25, 50, 7500. So CPU seconds per cycle is reported. And you can kind of see that the more CSTRs we have, the longer it takes. But in terms of the predictive power, right, of our model, when we have just 10 CSTRs, the purity prediction is inaccurate. But because the paper expected above 99.5% purity. So at least we need 50 CSTRs to match the purity of the paper. And then also the recovery, right, is about 10.47%, which the paper reported of slightly larger than 10%. So we think that 50 CSTRs was good, but and you can kind of see after you increase CSTRs to 75 and 100, the difference gets smaller. So we need more than 10 CSTRs for sure, but above 50, I think we're getting the right accuracy. So this is how you determine the number of CSTRs. It's to run a bunch of simulations to decide how many CSTRs you're going to need. And the next one, we actually wanted to simulate some non-ideal basic process, right? So there's some mass transfer resistance and also temperature. Heat of adsorption is pretty significant, right? So we actually simulated that, and then you can kind of see. Also, we threw in the equalization step, right? So the two pressures, high and low, comes together, it equalized, and then the lower pressure one gets pressurized and the other one depressurized, and then you do purge and you do high pressure feed, and then you equalize, depressurize, and purge, and then you equalize, repressurize, and feed, right? So basically, this is pretty complex PSA cycle that's going on with two adsorption columns, and we actually ran this simulation with non-isothermal heat effects, so you can kind of see the heat temperature profile during the high pressure feed step, right? So you start out with the lighter color, but then towards the darker color you progress, right? So heat evolves, right? Adsorption is exothermic process, so it releases heat to the environment, and then as adsorption happens, your system temperature goes up. It swings about 10 Kelvin. And then you can see some difference in the non-isothermal and isothermal predictions, which you can readily see from this plot, and they're pretty much not that significant because temperature evolution was within 10 Kelvin of but still it's really great to see that, you know, these non-isothermal simulations are capable of predicting these temperature profiles and yielding different results than the isothermal counterpart. And we did some testing about you know, numerical performance of these solvers, right? So we actually consider the number of failed integration steps as one of the criteria here, right? So and then you can see from the caption that for each PSA cycle, equalization, repressurization, depressurization, high pressure, low pressure, equalization, depressure, repressurization, low pressure, high pressure, right? It's cluster bar graph. So basically, the left bar is the no pressure drop model. The middle bar is the model using Argun equation, so momentum balance equation, and the right bar is the model using Argun's equation with modified parameter leading to larger pressure drop. So you can kind of see that the fraction of the number of failed steps, right? Because the shaded rectangles indicate number of successful, and empty means the successful integration step, and shaded means the failed, right? So you can kind of see, especially for the middle bar, the number of failed integration is more than 50%. But for the first bars, right, they are no pressure drop model. They generally perform much better in terms of, you know, dealing with failed number of failed steps in numerical integration. The smaller the number of failed steps we have, the better the numerical performance of integration is, right? So this was kind of nice to compare the numerical performance of different ways of calculating the volumetric flow rates inside the right-hand side function. And we also consider the further computational, you know, consideration here, right? So when we talk about further computational considerations, we're trying to speed up the integration, and one way to do that is to provide some Jacobian information for the OD15S solver. So we actually provided the Jacobian sparsity pattern, and that which significantly improved the numerical integration time. So which we're able to see from the table. It should be here. Yep. So basically, for flow-driven simulations, we have an option to use guess and check algorithm, which means we're just solving the linear program only when there's a violation or the guess in our flow direction has failed, right? So we can actually see that by using guess and check, you can substantially reduce the CPU time. And for pressure-driven case, you can consider specifying the Jacobian pattern, and you can see that there's a drastic difference even for this KJR neighbor's case, factor of 10, right? Reduction in simulation time. But these are really useful numerical techniques to improve our computational time in our work. Simulation, yeah. And finally, we can talk about advanced model features such as handling flow direction reversers. Traditional PSA models, they're not that robust in terms of flow direction flipping during the simulation, because flow direction is such an important concept here. Because when flow direction switches, I can illustrate this in our CSTRs, right? So when flow is going from the bottom to top, material from the bottom CSTR goes into the N CSTR, and material in the N CSTR goes out to the N+1 CSTR, right? But if flow direction changes, then now material from N+1 CSTR leaves the CSTR and enters N CSTR, and material in N CSTR leaves N CSTR and enters N-1 CSTR. So depending on the flow direction you have, you need to define the right upstream and downstream, right? Otherwise your mass balance and energy balance would be violated. So that's why our toPSAil is more robust. We designed our model to be robust against flow direction change because we used the notion of pseudo-volumetric flow rates. And by using the notion of pseudo-volumetric flow rates, you can kind of see that, all these pseudo-volumetric flow rates are so you see that when there's negative flow rate, like flow reversal happening here, the negative pseudo-volumetric flow rate becomes positive, but then your positive pseudo-volumetric flow rate becomes 0. When the flow rate is positive, then the positive pseudo-volumetric flow rate remains positive, but the negative pseudo-volumetric flow rate becomes 0. So you can kind of see the gray line is the volumetric flow rate, and then the pseudo-volumetric flow rates account for these, right? Volumetric flow rates for the Kozenik-Kalman equations also works in a similar way too as well. So to account for the flow reverser in our model, because our model is already written in terms of pseudo-volumetric flow rates. So that's one of the advanced feature in our toPSAil, right? Be able to handle the flow direction reversers, and we can actually control the process states too. So we actually use event functions to control process state. So for instance, when we do high pressure feed, we can either run this step until set duration of the high pressure feed time runs out, or we can set an event where it's saying that whenever the product purity coming out from the top end of the assertion columns becomes lower than the threshold, then we stop, right? So we can actually incorporate event function to better control the state, so things like when to stop the integration and so forth. And that event function has a ability to lower the number of cycles required to approach the cyclic steady state. So when you combine flow-driven simulation with events, you reach the cyclic steady state much faster than not using the events. And that's pretty much it. So we did a lot of including advanced modeling feature in our toPSAil simulator. And the framework is really intuitive if you get your, especially when we think about the pressure flow diagram too. It's really once you get used to this framework, you'll be able to start thinking like basically you'll be able to start thinking in terms of how these two assertion columns should interact with each other, as well as the other units in this flow sheet, and then what we need to specify to simulate which different types of PSA cycles that we want.